Hi guys, in this lesson we'll take a look at the extent of reaction. Now, to summarise the importance of the characteristic variable zeta, now this is known as the extent of the reaction, then we can use the following equation that is involved in a particular reaction. Now, in general, what we have here is based on the initial and final number of moles, and it's also based on the stoichiometric coefficient for a given species. And it will be easily possible to compute all the other numbers of the moles in the system after the reaction takes place. So in a chemical reaction, what you must always do is it always moles that can be related to each other. So for example, if we had A plus B goes to C plus D, and we'll say that this is 2 here and this is 3 here. Now these stoichiometric coefficients are in theory, these are the ideal scenario, so that means that 1 mole of A plus 3 moles of B would produce 2 moles of C and 1 mole of D. Now this is moles that binds all of these together. We can't use mass to bind these together because the mass of each species for 1 mole will be completely different. So you can see that in the GFM values in the chemistry data booklet or the grand formula mass of different compounds. So by expressing the values in terms of moles, it makes it easy to determine the actual number of moles we have within the system, both as reactants and as products. So that's why it's very, very important that it is in terms of moles. Now the extent of the reaction is based on a particular stoichiometric equation, and it denotes how much reaction actually occurs. Now the units would be moles reacting. So we're essentially saying that this value is how many moles of the system has actually reacted. And the extent of the reaction can be calculated by the change in the number of moles of a species that occur, and then divided by its stoichiometric coefficient that we've seen in the previous slide. Now for example here, if we consider the chemical equation for the combustion of carbon monoxide, then the signs of the stoichiometric coefficient to be used will conform to what the standard practice in calculating the extent of the reaction would be. Namely that the products would have a positive sign and the reactants have a negative. Now that features all throughout mass and energy balances in chemical engineering, and also equates to a lot of the other equations that we see. That when we talk about the reactant, we tend to associate that with a negative, and when we talk about the product, we tend to associate that with a positive. Now what we're saying here is that if we have, say for example for the CO2, then if we have the initial amount of moles of CO2 was say 0.5, and then the final number of moles would be 0.25, then the extent of the reaction would be that it would be the initial, it would be the change in these values divided by the stoichiometric coefficient here of 2. And that would then allow us to equate the corresponding values for the other components. So the more formal definition, and it's the same equation that we've seen, but the more formal definition would be that it is based on the initial concentrations of the reactants and the products. So Ni here is the number of moles of the species after the reaction has occurred. So in the previous example that we said, so for zeta, if it was, we say 0.25, then it would be minus, and then it would be 0.5 divided by 2, because Ni naught is the species at the beginning when the reaction starts, and then the stoichiometric coefficient is the value at the start of the chemicals, and then zeta of course is the extent of the reaction in kilomoles, for this case kilomoles reacting. So you would carry this calculation out and get the value of zeta. Now you can see that The reason we get a negative for the reactants is because this would be a negative quantity. However, if we look at a positive quantity, i.e. a product, then our zeta would become, say for example, we had the production of water. Then at the beginning, say our initial moles, Ni naught, was 0, and then Ni final was, say, 5. Then what we would have is it would be 5 minus 0 over, say, 2. Then we have a positive quantity, and that's why we assume that positive values are for the products and the negatives are for the reactants. Now, the coefficients of the products in a chemical reaction are assigned positive values and reactants assigned negative. That's just to reiterate what we just said before. And the Ni minus Ni naught is equal to the generation or the consumption of the component by the reaction. So if we can determine the extent of the reaction for the limiting reactant, we can relate that to all the other components. And the production or consumption of one species can then be used to calculate the production and consumption of any other species involved in a reaction once you calculate or are given the value of the extent of the reaction. So sometimes in a problem you might be given the value and have to work back the way. Other times you will have to determine it, but it only tends to work best if you carry it out in terms of the limiting reactant. So that's the end of this lesson. Hopefully this was helpful in understanding the concept of extent of the reaction. Please subscribe to the channel and leave any comments in the comment section below, and we'll hope to see you in another video.